Hi everyone, this is Maverick Pong, the Chemistry Guru. Now in this video, we want to discuss the concept on rate equation and order of reactions. Now in the topic on kinetics, the rate equation is probably the most important idea in kinetics. So we will need to be able to write out a rate equation based on the overall balance equation. And let us have an example involving this. If I have a very general equation here involving XA and YB to give me some products, usually in kinetics, the products are not so important. We're more interested in the reactants. Now, if I know that I have two reactants, A and B, then I can write out a general rate equation, which will look something like this. This rate of the reaction will be equal to a rate constant K multiplied by the concentration of A to a certain power M and the concentration of B to a certain power N. Now, of course, A and B will just be the reactants, depending on how many terms we have. If I have three reactants, by right, I will have three terms here. Concentration of reactant A to a certain power, concentration of reactant B to a certain power, then maybe concentration of reactant C to a certain power. Now, the power term here on the concentration of the reactant is called the order of the reaction, which is later what we will be focusing on. But in A-level syllabus, the order of the reaction, it will be limited to integer values, and we are only required to deal with order 0, order 1, order 2. So more on that in a while. So let's come back to this rate constant K here. Now this rate constant K is affected by two terms. One is the temperature, the other one is the activation energy. So maybe let me put this in here. K, the rate constant, will be affected by two terms, temperature and activation energy. Now, we know that when there's an increase in the temperature, the rate of the reaction would increase. So if I look at this rate equation, which in general talks about how rate of the reaction will be affected, it is affected by the rate constant K and the concentration of a reactant to a certain order, concentration of reactant B also to a certain order. So therefore, we know that if there's an increase in temperature, it has to be accounted for under K, the rate constant. And of course, I know that when there's an increase in temperature, there will be an increase in the rate of the reaction, right? So it would mean that when temperature increases, K would also increase. So what this means, as mentioned previously, when temperature increase, I will have a corresponding increase in the rate constant K. Now, how about activation energy? Now, usually how do I affect the activation energy of a reaction is if I want to lower the activation energy, what we can introduce is a catalyst, because a catalyst will provide an alternative reaction pathway with a lower activation energy. So if I add a catalyst, I know that the rate of the reaction will also speed up. So therefore, if I lower the activation energy, which means that it is easier for the reactants to be converted to products, the rate of the reaction will increase and it will be accounted for under rate constant K. So if I add a catalyst, the activation energy of the reaction is expected to decrease. So therefore, it will cause an increase in the rate constant K. So remember, when there's a change in temperature or when you're adding a catalyst and it affects the activation energy, effectively what you're affecting will be the rate constant K, and in turn it affects the rate of the reaction. Now for the rest of the discussion that we are interested in, and actually for the topic in kinetics, actually, what we will be focusing on is actually the order of the reaction, which is this term here, the power term, M, which is the order of the reaction with respect to A, N, which is the order of the reaction with respect to B. Now, both these two terms, we say that these are the order of the reaction, and it is restricted to, as mentioned previously, these three values, 0, order 1, and order 2. So in A-level chemistry syllabus, we are only restricted to order 0, order 1, and order 2. So the next thing we want to do is we want to determine what if it is a zero order reaction with respect to a reactant, maybe reactant A, what if it is a first order reaction with respect to reactant A, and what if it is a second order reaction with respect to reactant A. Alright, so let us run through this part by part. What if it is a zero order reaction with respect to A? Now if it is a zero order reaction with respect to A, then if I just substitute this order 0 into the rate equation with respect to A, then it will just look something like this. The rate is equals to rate constant K, concentration of A to the power of 0, anything power 0 is 1, right? So the rate will be a k term, which means that rate, it is a constant. So what this means is, if I convert this to a concentration time graph, then the shape of the graph is expected to be a straight line, and if it is a straight line, it will mean that the gradient is constant. Now we know that the gradient of a concentration time graph, it will just be the rate of the reaction. So if it is a straight line, it means that at this point here where the concentration of A is very high, the rate of the reaction is given by the gradient here. So maybe if I consider this point, the gradient will be this value here, and it is a certain value K. Now when the concentration of the reactant decreases all the way until here, and at this point, what happens to the gradient? This is the same value, right? Because it is a straight line, the gradient, it is the same. So therefore, the rate of the reaction is the same. So what this means is the concentration of A, it actually doesn't really affect the rate of the reaction. When you have a lot of A, the reaction is so fast. When you have very little A, towards the end of the reaction, the rate is still so fast. Actually, it is not affected by how much A there is inside the reaction mixture. So we know that this is zero order with respect to A. Now, in my opinion, I think it is more important for us to be familiar with the concentration time graph, because concentration is something that we can measure in the experiment. Time is, of course, something that we can measure in an experiment. So therefore, the first graph that we are expected to plot will always be the concentration time graph. So based on the shape of the concentration time graph, we should be able to predict whether this is a zero order, first order, or second order reaction with respect to A. So if it is a straight line, straight away we know that this is zero order with respect to A. Now next, how about first order reaction with respect to A? If it is first order with respect to A, then the rate equation will look something like this. The rate equals to a rate constant K, concentration of A to a power 1. So therefore, rate will just be a K concentration of A. So it means that the rate is directly related to the concentration of A. When you have a lot of A, or when the concentration of A is very high, the rate of the reaction is expected to be high. And when the concentration of A is very low, the rate of the reaction is expected to be low. Now actually this is more intuitive, right? Because in general, when we deal with reactions, most of the reactions that we experience will be something like this. At the beginning, when you have a lot of reactants, the reaction is expected to be very, very fast. As the reaction proceeds, when you have less and less reactant, then the reaction gets slower and slower until finally the reaction stops. So it is a little bit more intuitive for us to visualize the reaction in this way. And if I look at the concentration time graph, the concentration of A with respect to time, it is expected to be a curve, and it curves in this way. That means at the beginning, when the concentration of A is very high, the gradient, which again represents the rate of the reaction, is expected to be very steep. So if I have this point here, when you have a lot of A, remember the gradient is something like this, which is pretty steep, right? So this gradient will represent the rate of the reaction. A concentration high, the gradient is very steep, rate of the reaction is very fast. Now as the reaction proceeds, you will notice that the gradient actually gets more and more gentle, and towards the end of the reaction somewhere here, maybe at this point here, you notice the gradient becomes much more gentle. So when the concentration of A is low, then the rate of the reaction is slow. It is consistent with the rate equation here. Now, another idea that we would notice is for first order reaction, the half-life, it is a constant. Now the half-life of a reaction is defined as the time taken for me to reduce the concentration of the reactant to half of its original amount. So typically what we will use is, we will use 100%, 50%, and 25%. Because if I start off with 100% of A, then time taken for me to half the amount of A will be from 100% to 50%. So this time taken for me to decrease the concentration of A from 100 to 50%. So this time taken here will be the first half-life. Then the second half-life will be time taken for me to decrease the concentration of A from 50% to half of it to 25%. So from 50% to 25%, this will be the second half-life. And for first order reaction, half-life, it is a constant. So the first half-life that we determine versus the second half-life that we determine should be more or less the same value, or it should be an equal value. So half-life is constant only for first order reaction, And if half-life is a constant, actually we also have another expression that we can use, which will be this formula here. T half is constant for first order reactions, and it will be equal to ln 2 over rate constant K. So this will be useful because sometimes in questions when we are required to plot the graph, and the graph that we get, the shape is something like this, and we determine the half-life, and we realize that half-life is constant. So from constant half-life, we can actually determine or calculate the rate constant K using this formula, T half equals to ln 2 over K for a first order reaction. Now, I think it is also useful to keep in mind when we consider half-life, it is not only from 100% to 50%, 50% to 25%, because actually I can just start off with any point along this curve, then the time taken for me to halve that amount will just be the half-life. So what this will mean is, if you start off from 90%, the time taken for me to decrease the concentration of A from 90% to 45%, that is also counted as a half-life. So if I start off with 80%, the time taken for me to decrease the concentration of A from 80% to 40% is also counted as a half-life. So why are we interested in talking about this is because sometimes the values that they give us for plotting, we don't have enough points to plot our 25%. So maybe the shape of the graph in terms of data, we only have from the beginning 100%, maybe up to about 40% or 30%. So that means we don't have enough information to plot and extend this curve all the way down here. So we don't know what is the 25%. What this means is we will need to have another set of data within the graph that we have plotted to determine the half-life. So maybe we can use 100% to 50%, 90% to 45%, or maybe even 80% to 40% to get two half-lives so that we can compare the two half-lives to see whether it is constant or not. So remember, for first order reaction, the graph is expected to be a curve for the concentration of the reactant time graph, and if I determine half-life, the half-life is expected to be a constant half-life. Now finally, for second order reaction with respect to A, now the rate equation will just be K concentration of A to the power 2. Now the concentration time graph that we are expected to have again will be a curve. So at the beginning, when the concentration of A is very high, then the rate of the reaction is very fast, and eventually as the concentration of A decreases, the rate of the reaction will become very low. So what is different from first order reaction and second order reaction is, for first order reaction half-life it is a constant, for second order reaction T half or the half-life it is not a constant. So this graph actually it is pretty easy to figure out. If the shape of the graph it is very similar to that of a first order reaction, from the half-life, whether it is constant or not constant, we can actually determine whether it is a first order reaction if half-life is constant, or second order reaction if half-life is not a constant. Now finally, if I put everything together, if I consider zero order reaction, first order reaction, and second order reaction, actually one of the methods for me to determine the order of the reaction, it is to plot the concentration time graph, and from the shape of the concentration time graph and half-life, I can determine whether this is zero order, first order, or second order. So remember, from the concentration time graph, based on the shape of the graph, we actually already can determine the order of the reaction. Remember, if it is a straight line, then it must be a zero order reaction with respect to A. So if the graph it is a curve, then we know that it is a first order reaction or second order reaction with respect to the reactant A. So the next thing we do is we find half-life, which is the time taken for me to decrease the concentration of the reactant to half of its original amount. If half-life is a constant, then it will be a first order reaction, T half is a constant. If it is not constant, then it is a second order reaction. Alright, so that was the discussion involving the rate equation and actually how to make use of the concentration time graph for me to determine the order of reaction with respect to a particular reactant. So if you have learned something useful from this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. That's all for now. Thanks for watching.